Hello, I'd like to go over Pop Quiz 8 and some PEC diagrams that were on the daily quiz after the Pop Quiz. They all refer to Unit 3, Module 3 and cover most of the material that we expect you to know going into the test for Exam 4 for Unit 3, Module 3. This particular question asks, what's the major reason that the mixed state does not always have more configurations? This question is based on usually when you mix substances together. So you have a pure ion and you mix in water, means it becomes completely soluble. We fully expect there would be more possibilities, higher configurations, and that's what we usually expect, right? So mixed has more configurations, more possibilities, and this is usually the case, except, right? This is the except part. If Q1 times Q2, so the charges now, instead of being +1 and -1, or +2 and -1, if they multiply together and give you a number greater than 4, what happens is water will organize around it through its dipole. And so I'm going to show that here. So the dipoles for water, remember these are the partial positive charges and partial negative charges, they organize around the charges. And what that ends up doing is it lowers the configurations of water. So water, instead of having more possibilities of interacting with itself or with the ion, it loses the interaction with itself and it only interacts with the ions. And this overall effect causes less configurations in these high charge ions. And so the answer to the question, which is why is it that, what's the major reason, is that the solvent effect, the solvent due to its ion dipole or its dipole ion interactions are so strong, it loses configurations, and so water is more ordered, it's less, there are less possibilities for water since it's more rigid now in terms of around the ions. So we would pick C, right? That the loss of configurations of the solvent are due. That's the major effect of why these high charges are generally insoluble, because the mixed state is always at low configurations. We'll say more about that when we look at PEC diagrams. Okay, so this was about the trend with size. So let's keep in mind the neutral trend is that lithium, if we're going across the second row, lithium's the largest. And as we go across a row, since we're putting more and more protons, the electrons in general are going to the same shell, they get smaller as you go across a row. And that is the neutral trend. But with ions, all of the charges are different now as they go across a row. And you're being asked to compare lithium with nitride. And the lithium ion has 3 protons holding in, right, attracting 2 electrons. It's supposed to be a 2. And for nitride, there are 7 protons, and there has to, and they're attracting 10 electrons. And so the electron-electron repulsions, right, are overcome by the electron-proton attraction. And if there are less protons to electrons, then there's an overall increase in size as the repulsions becomes a more dominant term. And so the more electron repulsions there are, we would expect it to sort of puff out, be a bit bigger than lithium, which only has 3 protons, and remember that's attracting 2 electrons. So this would be much larger as the 10 electrons are repelling each other with only 7 electrons holding them in. And we would expect the answer to be the first one, which is that nitride has a larger radius than lithium plus due to the electron-electron repulsions and the higher electron to proton ratio. So it's really about electron to proton ratios. It's definitely not about configurations. It's not the same as the neutral, so A is the best answer here. And this is a problem that we spent a lot of time on in terms of ranking melting points. If you're ranking melting points, that means you're working with Coulomb's law. So let's write it out. That means we're looking at two different terms. We're looking at a numerator, that's the product of charges, and the denominator, which is a effect that going down a column, right? Because the only substances that have the same charge are ions that are in the same column of the periodic table. So we have sodium phosphide, that's sodium plus, and P3 minus. We know that because it takes 3 sodiums for every 1 phosphorus for it to be neutral, but also where they're at in the periodic table. Phosphorus needs 3 electrons, acquires 3 electrons to obtain the full octet, and sodium loses 1. Same analysis for sodium and sulfide. And then we have sodium chloride and sodium bromide. I'm going to divide this up because the only 2 pairs that need the denominator in this analysis are the 2 with the same charges. So that would be evaluating chloride versus bromide. But sodium phosphide, sodium sulfide, and then the general sodium chloride, we know that this is only the numerator, right? Only the numerator, which is only the charges. And if it's the charges, then the product of the charges, as that goes up, the melting point goes up. Because it takes more force, there's more force holding these ions together. And that's what we have to overcome in melting. And if we have to use the denominator, then as we go down a column, the melting point goes down because the ions get bigger, and the bigger radius is in the denominator, force goes down. So the melting point will always go down, will decrease as you go down a column. So that makes the top pick with the highest charges. The numerator is going to be 3 for sodium phosphide. And then out of the +1, -1s, which the numerator is 1, we would pick bromide, sodium bromide, to be the lowest melting point since it is lower, farther down in the column than chloride. And that gives us the answer. Lowest charge and largest ion, right? Gives us the answer C. Okay, so here we have a predicted solubility difference between calcium phosphate and calcium chloride. So we look at the ions. Calcium is 2 plus and phosphate is 3 minus. The product of that is 6. And that is greater than 4. Versus calcium chloride, which is +2 and -1. It's only 2. So if we look at that, that means that if the charge is greater than 4, we know that the mixed state is in the top left corner. It's at high potential energy and low configurations. We expect it to be insoluble. Let's take a look at calcium chloride. So it's +2 and -1. This is below 4. So we expect this to be soluble. And so depending on the information we have, we expect the mixed state to be in one of 3 possibilities: in the top right, in the bottom right, or in the bottom left. But any one of these cases would have a soluble feature, either at low temperatures, high temperatures, or always soluble. And so when you have a product less than 4, it depends on what the potential energy ordering is based on temperature solubility. But we know it has to be in one of those 3 regions. Less than 4, it has to be there, and so we would be able to anticipate. We would be able to correctly assign it if we had more information. So this is soluble, this is insoluble. So if you're greater than 4, you're always in the top left corner for mixed. If you're less than 4, then you are in 3 possibilities. It just depends on what other information you're given. So the answer is B, as we talked about in question 1, that the loss of configurations always raises lowers the configurations of the mixed state, and the strong ion-ion interactions will also, for the unmixed state, so the unmixed state now, remember, keep in mind, these are going to be strong ion-ion interactions, lower potential energy, more stable in the unmixed state. So both answers, B and C, are correct. Okay, so these are the two PEC diagrams that we talked about in that we had in our quiz. It wasn't part of the pop quiz, but these are questions you should be prepared for. And so if we're looking at this problem, so we have the unmixed state shown below as the solid plus pure water liquid, and we have the mixed state, which is now these are ions in aqueous form, so they're completely dissolved in water in the mixed state. So we have two charges, plus 1 and minus 1. So in general, we expect this to be soluble, and we expect it to be soluble because the charge is less than 4, and we see that the mixed state is not in the upper left quadrant for insoluble, it would be in the upper right. Okay, and so at higher temperatures, as we increase the temperature, we should access the high potential energy state, which is mixed. So we expect, and since solubility is a measure of how much mix there is, if we have more mixed at higher temperatures, we expect the solubility to increase. So we access the high configuration state. Remember, this is the most stable state in terms of configurations, because there's more ways to share the total energy around these configurations. So high configurations and low potential energy are always the most stable system characteristics. And so that means that we expect sodium bicarbonate to be more soluble at high temperatures. And in this case, we asked what interaction is most stable. And so we're looking at potential energy ranking now. So we expect the unmixed state to be the most stable. So that means the lowest potential energy are those of sodium ions and HCO3 ions. So the unmixed state has these interactions, Na plus interacting with the negative HCO3 minus, and water interacting with water. These are going to be the strongest interactions because they're at the lowest potential energy, versus the mixed state, which is water interacting with the ions themselves, right? This is at a higher potential energy or a less stable state. So we would select the interaction that's most stable is going to be sodium A, which it looks like I didn't pick A. So the answer here would be A. All right, so let's keep in mind a couple of the general ideas we used. In terms of charges, we expect the overall trend to be increase, right? Increase size as we get higher charges are going from plus charges to minus charges due to the increase in electron-electron repulsions and the lack of protons at negative charges to pull them in, and so they get a little bit bigger. So Q1, Q2, the highest value of the two charges have the highest melting point. If Q1 and Q2 are the same, then the highest in the column will have the highest melting point. Right? So that's the general rule. And the general rule here is that the mixed state will always be in the upper left corner if Q1 and Q2 is greater than 4. Very insoluble. Insolubility will slightly increase with temperature, but it will not become very soluble at higher temperatures. If Q1 and Q2 is less than 4, then depending on the information, the mixed state can be in either A, B, or C, and in that case, depending on temperature, the system will be very soluble. All right, with that, good luck.